Okay, good evening, everybody. This evening, for our evening lecture sessions, we have first presenter, Marc Bellemare, who is a researcher at Google DeepMind. And of course, he is very famous among our participants because everybody uses Allee environment. So everybody knows your work, and I think that maybe after your talk you will have a lot of technical questions.
Right.
I'm sorry for that, but people like that they have a very rich experience with your library.
Yeah,
so
I'm glad it.
just go on, and thank you that you accepted our invitation to give a talk.
Well, thank you for inviting me. I'm glad I could make it this year. It's actually really exciting to see so much work happening with the ALE and trying to push the boundaries of reinforcement learning. So what I want to talk about today is some of the recent work that we've done and looking at density models in reinforcement learning. And I'll make this a bit clearer, but I thought for you, I would do a bit something special. And before I go on with the actual new research, I figured I would take a step back and look at the history of the ALE and see where we're at today. So I don't know how many of you know this, but the ALE was actually inspired by a research project by Carlos Duke, who had a paper in 2008 where he used Pitfall as a test domain. And it was a very limited version of Pitfall where the agent had to cross the first screen. So something really, really simple. And so what happened now is that there was a workshop in Barbados shortly after this presentation, the same year. And Michael Bowling, my supervisor back then, had this idea of using the Atari as a suite of test domains. So this actually took a few years to take shape. He had a master student called Yavar Nadaf, who worked on the very first version of the ALE. I hope none of you have had the misfortune of downloading ALE 0.1 because it's a lot more crude than what we have now. So that went on for a while. Then I came in 2011 and actually made sure to package the environment so it would actually be a full environment. And I did some research over the next 3 years, showcasing the ALE, saying, we really should care about 60 games instead of just 1 game or 2 games, okay? And then we had this paper that we published in 2013, representing the ALE to the world. And this immediately led to some research, but of course the one you'll be most familiar with is the phenomenal paper we had in Nature in 2015, led by Vladimir and others, where we basically said, well, we can actually use deep nets to do reinforcement learning. And if you're not from a reinforcement learning background, you might take this for granted, but in reality, this paper really changed reinforcement learning because up to that point, we didn't have a way of coming up with good representations. And deep nets let us do this. So since then, you know, things have exploded. This has been phenomenal. Question before we move on to the actual talk, which is to say, let's do a bit of a checkup and ask the question, where are we at in Atari? And so what I've done for you here is I've put the 60 games that we typically use in Atari for evaluating our agents. And I've put them on a timeline based on when they were released. So the Atari itself, the video game console, the 2600, was released in 1977. And what you can see is that most of the games we have come from 82 or 83. Now the 60 games were sampled uniformly at random. So what that means is that there were more games made in the 80s than there were in the 70s. It sort of makes sense, right? But that's not the point I want to make. So the point I want to make is that if you look at this graph, and this is a very subjective graph in a sense, but what I've done here is I've listed all the games by order of date of appearance. And I've put a red check mark next to the ones where basically I'm better than most of the agents that I know. So this is a subjective measure. For example, skiing, it's debatable whether they're actually there, I'll agree. But you know, the red check marks for me, I can play better than the agents. For example, in Sequest, yesterday I had a score, I played Sequest for fun, and I had a score of 150,000. I don't think we're quite there yet. In blue, we have similar effects, but the agents might be doing very well, so they're solving the task. but they're not really playing like humans. So they're finding a score exploit. We've talked about this a bit in our NIPS paper on exploration. So the point I want to make is if you look at this graph, there's something very surprising that emerges, which is we're really good at all the games from 1980 and before. Actually, as a matter of fact, I would say we're human level performance better on all of them, or almost all of them. And once you move into the 80s, that's no longer true. And so what's happening here is that in the 70s, most of the video games were arcade-based, and they were very reactive, and you have to play and win the game immediately and collect score. And as you move into the 80s, the game designers themselves, using the same platforms, started making games that were more cognitively challenging. And what's very interesting is this is when you get games like Pac-Man, where you have mazes, or Venture, which is an adventure game, or Gravitar, Pitfall, Montezumas Revenge. Our agents are still not nearly doing as well as humans do. And actually, if you look at 84 and after, we're not very good at these games at all. There's fewer games, of course, too, but we're really not good at these games after 84. So by the way, in 83 was the video games crash, so very few games were released for the Atari after that. But I sort of want to say, and maybe this is something that maybe matters for you today as well, which is I feel like most of our agents are stuck in 1983. And that's where the next step needs to happen in Atari research. So hopefully you guys can make some progress on this. So let me start with the actual content of the talk. And the point I want to start at is a quote by Rich Sutton, where if you ask him what reinforcement learning is about, he's going to say, reinforcement learning is about maximizing some value function, right? So let's tease this apart a bit. This will be familiar for all of you, but just in the interest of keeping the story, when we think about RL, we have an agent interacting with the environment, and there's this transfer of actions to the environment and state and reward back to the agent. Okay, and then normally we look at the Markov decision process framework, where we have a reward function, a transition function, a policy, and a discount factor. Okay, so nothing too surprising here. These are the basic building blocks of RL as we know it. Okay, and so when we think about a value function, then that's the QPy, the Q function would be the expected sum of discounted rewards under the transition function and the policy. Okay, so that's what Rich Sutton means when he says maximizing some value function, I think. Okay, so how do we think about this in terms of mathematics? Well, usually we'll use the Bellman equation to relate the Q value QPy of a state with the Q value QPy at the next state, right? And this is this equation which you'll be familiar with. The Q value is the reward plus the discounted next state value. Okay. If we want to learn this Q value, then we'll use SARSA or SARSA lambda, where we'll replace this expectation of a transition function by just taking a step in the direction of the target, right? So we go, my Q value is the current Q value plus a small portion of the TDR, which is going to be the reward plus the discounted next state value. Okay, and so the backup looks something like this. We take a step in the environment. For example, we're playing chess, and we observe a transition. In this case, maybe our opponent replies with E5. And we also get a reward. In the game of chess, that reward is usually 0, but that doesn't matter too much. Now we query the value of the state and the action of the next time step, and then we backpropagate this into QSA. So that's how we learn about Q value. In RL, we actually want to find optimal control, so we want to maximize the reward. So there's the equivalent version for optimality of the Bellman equations is when we replace, instead of keeping the policy fix, we take the max. And taking the max, if we look at this from a online perspective, then this leads to the Q-learning algorithm, where the TDR will become the reward plus the discounted next state max value. Okay, and these are the very basic building blocks. Of course, now there's been many improvements over these ideas, like double DQN, persistent Q-learning, advantage learning. But I'm just going to stick with this for today. Okay, so the point I want to make is that these are the basic building blocks, and all of these basic building blocks implicitly assume that when we can represent the value of each state action pair exactly. And it's exactly where deep nets have had so much success, is we can't actually do this in practice. So instead, we have to use a parametric function class to represent our Q function. Okay. And so what does that look like? Well, now we start with a Q function parameterized by theta, and we'd like to learn theta prime, which reflects this Bellman update that we've done. Okay. The problem is we can't just directly backpropagate the Q function straight into a parameter class, because usually the Bellman update will not belong to the parameter class. Instead, what we have to go is go about by what's called a projection step, where we take the result of the Bellman operation and then we bring it back. Now, if you're doing gradient descent with a deep net, that projection step is implicit in there, but it exists, right? You can never represent a value function which is outside the boundary of what your net can do. This is why so much work gets done on learning the right architectures to sort of increase the function class. Okay? So that projection step is actually problematic. Okay? But before I talk about why it's problematic, let's just review very quickly the kind of projections or the kind of function classes that people have used. So if you go back to Jerry Tesoro, the TD Gammon in his backgammon player, he was using a neural network that was 80 hidden units, right? That's quite tiny. And then if you think about it, clearly in that case, we can't represent all the value functions. So the projection step matters quite a bit here. Now you can move, look at the deep nets. We have bigger nets, but the problems are also bigger, so the same questions arise. And just to say that this issue is not just about deep nets, if you look at different function classes, for example, linear value functions for Atari, this is work that my PhD student, Marlos Machado, has worked on, then something called blob prost, where you decompose the screen into image components, image patches, and then you encode the presence of colors in each of these cells. That actually works quite well as well. And that has nothing to do with deep nets, but again, there's a projection step. And we understand the linear case very well now enough to know that the projection step is quite problematic. Okay, just to leave you on a note to say this is not just about Atari or functions. I was involved in a project called not the study project, but work with the study data, where we were looking at major depressive disorder and trying to come up with sequential decision treatments for major depressive disorder. This was a batch of data that had been accumulated based on a clinical trial. And we were trying to fit this clinical trial data to come up with the best sequential treatment for depression. Okay, and in that treatment, there were 4 treatment phases, so you can think of it as 4 time steps and 13 different actions. But now, once you move to a domain like this, we had 4,000 patients to deal with. That's very, very little data. So you can't fit this with a deep net. You can't fit this with linear approximation. So in this case, we had to use a very different kind of function approximation. We used kernel-based methods, right? And they work quite well. Again, what I want to emphasize is issue. Okay, so this projection issue is endemic to RL. And so the reason why this matters is because I think the way we often think about reinforcement learning is exactly the picture I've given you. Function, we compute that value function, and then we sort of blindly regress back, trying to match the value that we've computed. And that's, compared to the tabular case, that's leaving a lot of things by the wayside. In a tabular case, you're counting the number of times, you can count the number of times you've seen a point. So you would have a handle on how often you've been to a state, and through that, to be able to know about the uncertainty about your value function. Okay. Another problem is learning can be very slow because you, again, don't have a good sense of how often you've seen data point. You might need to bootstrap details over multiple iterations. Okay. And as I was hinting to, when you look at the control case, where we look at the Bellman optimality equation, there's a lot of divergence issues that arise. And that's one of the major open areas of research in reinforcement learning, is dealing with divergence. Advantage learning or double DQN are exactly trying to get at that problem, right? So the question I want to ask today and try to answer is, tabular RL, both in the intuition and the tools it gives us, is very powerful, but it doesn't scale to the realities of the real world. So can we recover the good part of tabular RL without for the Q function? Okay, so my answer here is going to be to use density model. So what's a density model? Well, a density model is going to be something that maps states to probabilities. So instead of mapping a state to a Q value, or state action pair to a Q value, we're just going to ask the question, what is the probability of that state? And I'm going to leave this vague for now, and I'll make this more clear in a bit, but you can think of using the CTS model, which I've used. You can think of using Pixel CNN, any model a generative model that assigns probabilities. And the intuition is that if that model is trained on all the data we've ever seen, apart what's frequent and infrequent by looking at the probability. A highly probable state should be a more frequent one. Otherwise, your model is doing a terrible job. Okay, so let me give you a bit of math. We're going to talk about a finite set X. Okay, and we're going to talk about the data x1 to n coming from that set of data. And I'm going to write the probability of a state as rho n of x. And I'll make clear what that means. But for now, this is the probability that the model assigns to x after training on that data. That's the way to think about it. Okay, and I'm mostly going to talk about just x's, but you can think of this also in the context of state and actions. Okay, so let me talk to you about a very simple density model, just to ground things a bit in concrete terms. So the CTS model is a model for Atari frames that I worked on 4 years ago now. And what the CTS model does is it starts with an Atari frame, okay, and it decomposes the frame into image patches of equal size. And now what we're going to do is we're going to use a separate predictor to assign a probability to each of these image patches. And we're going to now basically compute the probability of that frame as the product of all the predictors at each frame. Okay. And what we're going to do to predict each of these guys is use a powerful model called the CTS model. The CTS is actually a tree-based model. It's a variable order Markov model to guess at the probability of a patch in patches. Okay, so it's a kind of probabilistic generative model. And so just to make it clear, what we're going to do is predict each image patch. Think of these patches as pixels if you want. Each image patch using a local context, which is the 4 blue squares around the pink square. That's a really, really simple model. And one of the points I want to make here is using a really simple model, you can get really good results compared to the kind of complexity you need to build other kinds of models. All right. So you can either do pixel level prediction, where you would actually look at every pixel, compute a probability distribution over all the pixels, and then try to reconstruct the image on a pixel level. Or as I said, you can use patches, which then you have more patches to predict. Sorry, as in there's more possibilities for these patches, but there's fewer patches to predict per step. So how can we use this in practice? We can use this, or we can also, as we've done with the NIPS paper, you can take a raw Atari image, downsample it, turn it into grayscale, and that makes it easier to predict. So all of these are good ways to construct your density model. You might do some pre-processing ahead of time. Okay, so let me show you some samples from Atari frames generated by the CTS model. So you have the movie is showing you frames from Freeway. Okay, and you can see that these frames are not actually very good, but they're incorporating the core structure of Freeway, which is that there's a dotted line in the middle, right? The dotted yellow line and lanes, and there's cars. But what I want to stress here is that that model is actually really bad, but it is giving us a probability where it mostly outputs reasonable frames. You can also look around the movie. There's screens from Pong. This is a model trained maybe on 1 million frames. And at the top left, you have the actual frame. This looks like a reasonable Pong frame. Now, if you look at the other examples are generated by the model. And immediately you'll notice there's something wrong with these frames. In one of them, there's no ball, but there's 3 opponent paddles. If you don't know Pong, but I'm sure you do, you're the right-hand player, the left-hand player is the computer. Right, so you get this left-hand paddle, there's 3 of them, or maybe in one of the frames there's 4 balls and 2 of your paddles. So the density model will produce if it's not too good. What I'm going to show you is even with bad density models, we get really good results. And so before I go into that function, okay, you can easily combine them. Because they're probabilistic, you can bring in a lot of tricks like switching, extending this using variable discretization of the space, skip contexts. All of this is because probabilities are well behaved. Unlike the value functions, right, and all these divergence problems, they just play nice in general. Okay, And one cool thing is you can use any compression algorithm to turn it into a density model. And I'm not going to go into details about this, but I think that's one powerful thing about this idea. So let me now tell you about one of our projects that uses density models. And that project is called Compress and Control. This was published at AAAI 2 years ago now. And the idea is to step back and think about reinforcement learning in a different way, okay? So what we did here is we wrote down the value function, Q pi SA, and we said, all right, it's an expectation over a sum of rewards. Let's make the problem a bit simpler, and let's look at finite horizon undiscounted, okay? So there's a sum of rewards, and we can think of that sum of rewards as a random variable. Instead of thinking about just the values we get, it's a random variable, and we're looking at the expectation of that random variable. Okay, so if we do a bit of math, we can write down the Q function as an expectation. And the expectations is that's what the definition of an expectation is. The expectation is the sum of all the possible values times the probabilities of these values. The mu here should be a p instead. Let's assume for now that there's a finite number of these returns that we can have. So we write this expectation, but now we can use Bayes' rule. We say the probability of the random return being z, given that I started in S and took action A. We know by Bayes' rule that's going to be the probability of S given Z and A times the probability of Z and A. And that's what this equation is saying here, okay? The question is, what does that probability even mean, okay? But one way you can think about it is it's a kind of generative approach to reinforcement learning, where instead of learning to map state and actions to returns, we learn to map returns and actions to states. And we're going to do this, of course, with a density model, okay? So we're going to have two parts to this value function. The first one is we use a density model to learn, conditional on the return and the action, what's the probability of a state, that model. And then we can compute the probability of a return given an action. That's fairly easy. We just count. We just multinomial distributions will do it for us. Okay. So hopefully that makes sense, but I'll give you an example to sort of explain what goes on under the hood. Your value function, if you will, now, is going to be composed of a number of density models, and they all start being exactly the same. You have one model for each action and return pair. So for example, if you're playing Pong and you have returns of 0, 1, or 2, and you have up or down, then you would have 6 models, okay? So what we're going to do now is look at how we can train this value function. And the idea is to talk about the random variables that are involved here. Basically, what we're saying is the probability of a return. The return is going to be the sum of the rewards into the future. And we're going to look at the probability of the state that happened m times steps ago, conditional on that return. So let me give you a bit of an example, a moving example. You have your big model at the bottom, which is the set of all the density models that you have. Okay. And now you have a trajectory that happens. You start on the left and you move forward. You're taking an action, moving the next state, action, next state, receiving a reward. Okay. We sum up these rewards, and that defines the return. Now we're going to look up in our table of density models to find the model that corresponds to a return of 2 and an action, in this case, going up. And we're going to feed that model, we're going to train that model on the frame that corresponds to the action we just took. Okay? If that doesn't sound crazy, it should sound crazy. It is a crazy idea, but it works. And let me show you that it works by effectively playing. I'm going to play for you a movie of an agent training with this approach on Pong. Now, before I play the movie, I'll tell you about the model. So we have the CTS model. In Pong, you end up having 5 or 6 returns ranging from -3 to 2. Okay, and the actions, as you know, there's actually 3 actions: up, down, and fire. And so what you're going to see now, I'm going to start the video. What you're going to see is the agent sped up, I think, a factor of 5. I've just started this agent. This agent has never played a game of Pong in its life. Now what it's doing is it's playing the game, and you're seeing in real time, you're seeing it learn. Okay, it's playing the game, and there's a horizon of 80 frames. And after 80 frames, it's going to look at the return it's observed and train its density models to predict which state this corresponds to. And we're going to use that, using the math that I've just described, we're going to use these density models to estimate the value function. And all of you guys have been working on Atari for a while, so hopefully you'll be impressed by this result, that in real time, we're seeing this agent clearly getting better at playing Pong, right? It's already getting 10 points, 11 points. It's played maybe 7 episodes, right? So for me, that's highlighting the power of a density model is, and I don't have time to go into all the details why this is the case, but these models learn blazingly fast. What the model is doing is saying, I have to make a choice. Do I go up or down? And I'm going to look at the current state and say, is it more likely that I get a reward of 1 or a reward of -1 in the state? But I don't know that answer. Instead, I'm going to ask the question, is it likely that this state leads to this reward? Let me condition the reward or the return and ask how likely this state is. Okay, so there you go. That's the agent playing. I think that's the end of the video. After 13 episodes, this agent wins its first game of Pong. So that's the power of the density model. Look at a different video where it's a bit, what I'm going to do here is highlight the patch, the image patch, that the model thinks matters the most for its value function. Okay, and what you're seeing is the model is highlighting either the ball or the computer paddle or your paddle. And when I mean highlight, I mean here we're going to actually do a sensitivity analysis where we replace one of the image patches. Sorry, we don't replace it. We query all 3 models and we say, if I were to remove that patch, how would that change your value function? Okay, and doing this, we get this very nice visualization that the density model knows the parts of the screen that matters, even though we never actually explicitly had it learn features. It just puts more probability on the correct situation. Okay, so that's great. And these results, we had them, what was it now, 4 years ago, or 3 years ago, 3 or 4 years ago. And we've been very excited about these results. And you can look up in the paper how this works. I want to make a link between compression and density modeling because that was the intent of the paper. The idea is when you're compressing a file, the way you compress a file is if you're doing sequential compression, you take your data and you map it to a bit string. And if you have a new file and adding a new piece of data, you'll have an excess bit string at the end. And you can think of the excess bit string, if you exponentiate it, as the probability of that data conditional on everything else you've seen before. Okay. So people have used this for classification before. The way you can do this with classification is exactly by compressing xn+1, the new piece of data, using either the data on the left or the data on the right. And then you can use this back exactly the same way, using Bayes' rule, to assign probability to the actual labels. Because we assign a lower probability, so a bigger big string, lower probability, to class B, that means that it's more likely that we have a data from class A. Okay, so that's how we're doing compression control. That's the gist of the idea. You can think of it as planning as inference, where we're saying, again, in state S and take action A, will I receive Z? We ask the question, the reverse question. How likely am I to be in state S if I take action A and observe Z? Okay, so that's compression control. And this was a while ago. In many ways, we knew then that the density models were very strong, but they also had drawbacks. And it was only in 2015 that I started looking at these models again, at the end of 2015, when we got interested in exploration. And one thing that was clear is that we hadn't really sorted out what the semantics of these output probabilities are. But when I said the model assigns a probability to a frame, what does that mean? Suppose I vary x over the state space. What happens to the probability? Suppose I give you more data. What happens to the probability? So we started thinking about this a bit more. And we decided that it should be the case that if the model assigns a high probability to a frame, then that frame must also be more frequent. So there's a relationship, we would like to be proportional relationship between probability and frequency. And so we had some early experiments where we're trying to show this. And this is the game called Qbert, which you'll be familiar with. In Qbert, you have the orange agent that's trying to navigate this pyramid to collect points. And this is the agent on its very first playthrough. And on the left-hand side, you have a green bar. And the green bar is reflecting the negative log probability that the model, the density model, again, the CTS density model, assigns to the frame. On the first run through, that negative log probability is very high because the probability is very low. Okay, so what if we train an agent to play this game for a while and play it now again? And this is the same agent, but having been trained on Qbert. This agent has actually been playing for a while, and this episode is the first episode where the agent reaches the second level in Qbert. Okay, so the second level is going to happen once all the blue tiles have been swapped to be yellow. Okay, so this agent is quite good at playing this game. Now you'll notice there was a flash of green, so the bar is there. It was just very low. Now, as the agent is getting towards the end of the level, it starts to say, hey, these situations are novel. I haven't really been in this state before. This seems very new to me. And you have this very nice progression as we're getting closer and closer to finishing the game, this signal is going up, okay? Reflecting that the situation is less and less novel. The second level in just 1 second. Okay, it's going to happen. And look at this. Immediately when you come to the second level, the agent knows, I've never been here before. We looked at these results and we thought, there has to be something we can do with this. So we struggled for a while because it turns out that the raw probabilities aren't enough. And the problem is if you just plug in that data into a density model, the log scale of the probabilities is going to depend on a number of things. If you vary x, the shape of x, it's going to vary in terms of the dimensions, the number of pixels you have. It's going to vary in terms of the model class. Actually, it's going to vary in terms of the game you're playing by quite a bit. And it also depends on the rate of learning. So if your model learns more slowly, those probabilities are going to change slowly. They're not really going to reflect the frequency at which your model is learning, at which the number of times you've seen a state. So the solution was to come up with a new concept called the recoding probability. And what the recoding probability says is, we're going to start by doing a forward pass over our model. That forward pass is going to output the probability of the frame. Now we do a backward pass where we train the model on that frame. And then we do a second forward pass. And that second forward pass gives us the recoding probability, which is the probability after we've trained on the model. Okay. Now, in reality, with the CTS model, we get this for free, as in we do the counterfactual. We don't actually have to train the model. We can query the model directly, say, compute the counterfactual, tell me what that recoding probability is. Some models can do this for free, some models can't. The CTS model can give it to you not for free, but without needing to actually train the model. Okay, so now that we have these two pieces of data, what we did is we said, let's pretend that the probability corresponds to a ratio of two quantities. One that is the pseudocount at x, not the real count, but the pseudocount, divided by the total number of counts, also total pseudocount. And then let's assume that the recoding probability increments both of these by 1. It behaves like a count. All right. The way to think about this is we're trying to get back to the tabular case. In the tabular case, if you learned a density model and you said, what is the relative frequency of the state? You would say the number of times I've been to that state divided by the total number of steps I've taken. And this is what we're trying to do here. Come up with a relative frequency, or rather, reverse engineer the relative frequency back into counts. So we have two equations, two unknowns. We can solve the system, and we get the pseudocount equation. Okay. And what I want to point out to you is there's a term at the bottom, which is the difference before and after training, the recoding minus the coding probability, that difference encodes the rate of learning. And that's the part we were missing when we just had one probability, okay? So what's really cool about this is you can view this from the lens of intrinsic motivation and find out that there's actually a lot of relationships between what people had been doing in the past and what we've done. So if you talk about prediction gain, which is the difference in log probabilities, then the pseudocount is related to the prediction gain according to the formula in the middle of the screen. And then we can use this to derive bounds on how the pseudocount relates to prediction gain. And what's really cool is that we can do the same thing for the quantity called information gain, and again derive a bound. And both prediction gain and information gain have been used in the past to do exploration. So what that means is we know we have the right kind of quantity in a way. The pseudocount is related to things that people normally use. We can use it inside a count-based exploration scheme, like model-based interval estimation, which basically says, if I want to explore, I'm going to add a reward bonus, which is inversely proportional to the square root of the number of the pseudocount at x. Okay, and that makes sense in a tabular case. It's just going to be the regular count. Okay, and you can do the math and verify this for yourself. What's also really cool is that we know that pseudocount is the right quantity, and we know from doing the math that prediction gain and information gain are actually can be insufficient. Now, this is a theoretical result. In practice, they might still work really well, but I can come up with examples where prediction gain isn't going to be enough. So you really need that pseudocount to explore optimally. Okay, so these were pretty cool results. It sort of justifies this crazy contraption of a pseudocount. Okay, so you'll be familiar with this video, possibly. This is a game called Montezumas Revenge, and of course it's one of the hardest Atari games, right? So we all love Montezumas Revenge. This is me playing just to show you how difficult this game is. What makes the game hard? The first thing that makes the game hard is that it's really easy to die. If you make a misstep, you're going to, unlike a game like Freeway, for example, that misstep is actually going to cost you your life. So epsilon greedy as an exploration strategy doesn't work very well. Okay. The second thing that makes this game really hard is that the rewards are really sparse. If you think back about that timeline that I was showing you at the beginning of the talk, most of the early games have this property that there was a lot of score. In Space Invaders, you get a point every time you shoot something down. Okay. Now that's not true if you play Montezumas Revenge, and I think it's a trend that as video games got more complicated, this score, which was basically designed for arcades, so you could maximize your high score in an arcade and be the top dog at the arcade, that went away. People played those games for fun. They didn't need the score anymore. If you look at Pitfall is even worse than Montezumas Revenge in that sense, right? So we got really excited about trying to crack Montezumas Revenge. Okay, and if you're not familiar with Montezumas Revenge, let me walk you through it again. Montezumas Revenge, there's 3 levels. Each level is 24 different rooms. And to get to the end at the bottom left, you have to basically navigate this maze, pick up the key, open the door, jump over stalls. Even me, after playing this game, I've probably played it 100 times now, 150 times, if not more. I still make a lot of mistakes throughout this game. Okay, so it's quite a hard game for RL agents and even for humans. So we set out to crack this game, and we managed to get a good result by basically three components. And I want to emphasize there's 2 of them actually here that matters the most. The first one is the pseudocount bonus. So this exploration bonus really makes a big difference. The second one is actually number 3 here, is the Monte Carlo mixing. And the Monte Carlo mixing makes a big difference because we know this from theory, that if you do a one-step Bellman update, you suffer a worse approximation error. And I don't have time to really go into details here, but it was a hunch we had that the Monte Carlo mixing would be really good. I think it explains, that kind of idea explains the success of algorithms like the retrace algorithm that we've worked on, or n-step returns that have also been very successful, or policy gridding methods that directly use the return. So there's a cost to one step back up, And moving away from that cost is very useful. And of course, we also use double DQN, which stabilized the process a bit. That was a bit less important, but was still quite useful. So you might have seen this video. I'll play it again. This is the video of our agent after training playing Montezumas Revenge. And I think this is after 50 or maybe 100 million frames. And the agent has basically learned to play better than a human, at least at the beginning, right? It's doing the right things. It's picking up the sword. Now it comes here, and it's going to wait for these electric gates to open before it goes through again. And it's learned a sort of stationary jog where it waits in place and just waits for that for those gates to open. And there you go. It's going to come down here. And I want to bring your attention. What's going to happen? Oops. What's going to happen in this video is, as the agent gets to the end. Oops, that's a bit too far. As the agent gets to the end, now it's going to come to that dark room, pick up 3 gems, and now it's done. And the way humans usually play this game is they go and pick up a torch, and now they know that there's 3 gems. Now this is an RL agent, so the robot doesn't need a torch. It knows there's points. It just goes and gets the gems. But if you notice, it does know something. Once it has picked up the gems, I'll come back and play it again. It knows it's picked up the gems, and it comes back. Only then does it go back on its steps. So that means that agent has actually learned to look at the score to decide when it's picked up the gems, which I think is pretty cool. And that's the end of that result. That's where our agent sort of ends. It's still an open question as to how to crack Montezumas Revenge completely and get out of this room. But I'm quite excited to see if we can do it. So if you look at sort of the results we had in the paper, it's sort of obvious from looking at the learning curve that we've done something good. Both DQN and optimistic approach were at 0. Okay, and just adding the pseudocount bonus and the Monte Carlo return. I should point out DQN here is also with the Monte Carlo return. That just makes all the difference. So for Montezumas Revenge, this was a huge success. Okay, and I want to show you sort of the progression of the agent, the exploration strategy. So at the top you'll have DQN. At the bottom you'll have our agent. And what I'm going to show you is all the rooms that have been visited over the 100 million frames that this runs through. And so I'm going to start this now, and a room will appear once we've been there at least once, and it's going to fade away when we stop going there. So let's start this video and see what happens. I mean, it's immediately the pseudocount agent goes out and explores this world, right? It's not even a competition. And this is why we get this result. This is why this has been so successful. And you see that actually after a while, the agent stops exploring the left-hand side. That, for me, is the most exciting part. This agent kept exploring for a little while, then it stopped going somewhere because it decided it should go somewhere else. And that's the property you want of a really exploratory agent, is it knows when it needs to stop exploring. Now, in our case, I think our agent stops a bit too early, but that's something that we need to work on, right? So that was a pretty cool success. There you go. So that was the pseudocounts idea. Now I'm just going to end with sort of a connection between these two ideas and coming back to density models. When we did the compress and control now 4 years ago, we knew there was a problem with our approach. It was a very subtle problem. But when you play Pong or any game, some returns happen more often than others. In Pong, you get 0 most of the time. Okay, same thing for Montezumas Revenge, for example. That means that one of your models has seen more data. And we guessed that the probabilities that these models were outputting were skewed by how much data they had seen, because they're Bayesian models. Okay, and I'm going to spare you all the derivation, but the short answer is if you write down the compress and control value function, you can rewrite it in terms of the pseudocounts. Okay, and what you get by doing this is you get out that the probability of a state given a return is going to be proportional to the ratio of pseudocounts computed by the same density model. So there's a very close connection. But there's a term that multiplies this ratio. And that term is a warping factor. And the warping factor depends on how much data each of the models has seen. So for me, that's a really exciting result connecting these two ideas. There's a very close connection between the two, but the pseudocount lets us correct for data discrepancies. Okay, so that clearly suggests trying to do this idea of using just the pseudocounts without the warping factor, and we're sort of looking into this right now. But it's a neat little idea that should improve results performance a bit. So that's that. Just to conclude this whirlwind tour of density models, I think the take-home message here is that in using density models, we get generalization, which we need for practical reinforcement learning. But we're still preserving the spirit that we have in tabular RL or count-based RL, where we're saying, how many times have I been somewhere? How certain am I about this? Can I reason about the fundamentals of my data? The value function. Okay, and I think that's why density models are actually going to play quite an important role in reinforcement learning in the coming years. So on this note, that's going to be the end of my talk. Thank you very much for listening to me. These are some of my collaborators that were involved in these projects, most of them at DeepMind, and Marcus Hutter has also contributed some of this work. So thank you very much. I'll now take questions as you see fit. Thank you.
Okay, thank you, Mark. So questions?
Hello, thank you for the lecture. I have two questions, one
Yes.
about density models and one about ALE, technical question about ALE. So first question, in your work with pseudocounts, you used context tree switching as sequential density model, and you wrote that it was a simple model, but have you tried something more simpler, for example, empirical distribution of pixels, like empirical counts? Have you tested it? Was it good?
Yeah, that's a very good question. Maybe I can answer your first question, then I'll answer the ALE question.
Okay, second question.
Go on.
Okay, second question about ALE. And as I know that there are some stochastic options in ALE, for example, repeat action probability. And I was just interested about how your colleagues at DeepMind report the results of new method, which settings they use. Do they set repeat action probability to 0 in ALE, or they use it as 25%? Yeah,
right.
Because it's not clear from articles, and maybe you can tell it. Yeah.
That's a very good question. So let me answer the empirical question. I'll come back to the ALE question in just a second. So for pseudocounts, you were asking if we had tried empirical counts. Now, there is one model in the compression control paper where we used effectively a model that treated each pixel independently. So you can think of this as empirical counts, except we still have generalization because we're not counting the whole frame. And you can play a decent game of Pong with this, with patches, not pixels, but patches. But we get much better results with a better density model. We did not try it with exploration. That's an interesting question. We should try, maybe. It would be a very, very simple model. Now, I know that if you just use the empirical counts over the actual frame, that's going to fail. Because I'm sure as many of you have tried, every episode you're going to see new frames in Atari. I think the rate of new frames might be 50 or 60% on average, depending on the games. So a straight look at the screen approach doesn't quite work, which is reassuring, right? So let me answer now the stochastic question. It's still a work in progress to gain complete acceptance of it, but most people here would agree with me that it's a good thing to have, because it highlights, but it forces you to have a better, more robust algorithm. And I've seen, for example, there's certain games where stochasticity helps DQN, because a Qbert, because now you have to be a bit safer with your policy. I'm expecting that going forward, most of the results should be reported with a stochasticity. If they haven't been in the past, it's true that this is still a confusing thing. Now, I strongly encourage using stochastic execution, I think as we call it, just because it avoids the pitfalls of finding deterministic solutions that break very easily. Now, if you have any feedback on this, please feel free to email me or Malos Machado or Michael Bowling. We're always happy to hear feedback about this feature, the stochastic execution. And I'm also happy to defend it more thoroughly. Hopefully that answers the questions.
Yes, thank you.
You're welcome.
Okay, any more questions? No more questions about Ali? No. So thank you, Mark, for your talk, and thank you for your work on Atari learning environment.
Well, thank you very much for inviting me today. It's been a pleasure. Do keep me posted with the competition results. I'm very excited to see what comes out of this. And let me know how it goes.
Yeah.
All right. Thank you very much.
The results.
Have a good day.